A rhombus is a parallelogram with all four sides equal in length. So you can see the ticks indicate the equal lengths of this parallelogram. Like in all parallelograms, opposite sides are equal in length. Like the AD would equal BC. But it's not true, of course, in general that AD equals DC. AD and DC are normally different. They don't have to be the same. But what we can say is that DC is always equal to AB in any parallelogram. Now we want to prove that the diagonals intersect at 90 degrees. So we want to prove that this angle in here is a right angle. If this angle is a right angle, then the one that's opposite is also a right angle. Opposite angles are equal. Also, the one angle that's next to this angle is 90 degrees, because these two angles must add up to 180 to get a straight line. So if this angle is 90 degrees, then the one next to it has to be 90 degrees, and of course these are opposite. So if one of them is 90, they're all 90. Now, what we should try and do is just mark in angles that we know are equal. So rather than calling the angle BDC, say, for this angle here, I'll just call it M. It's just much easier. You can always revert to giving it its proper name. Well, its name using points on the arms of the angle at the very end. But for now, I'll just call this angle M. I'll call this one N. M equals N. Why? Because they're a pair of alternate angles, or Z angles. This line is parallel to this line. Now notice here that this angle, which I'm calling P, is equal to N. Why is that? Well, they're angles in an isosceles triangle. Triangle DAB is isosceles, this triangle here. And these are the angles that are opposite equal sides. P is opposite this side and N is opposite this side. So the angles that are opposite equal sides are equal. Now notice that what we've got here from these two equations, both M and P are equal to the same thing, namely N. So they must be equal to each other. So P must equal M. So that's worth noting. So we've proven that these two angles are the same. Now that might come in handy later. Now we can do something similar with angles R and S. Now you might wonder where this is going. I'm not 100% sure myself actually, but we just keep going with what we know about parallelograms until hopefully we can prove the result. Now R and S are another pair of alternate angles. So we have the Z shape again. This line is parallel to this line. Covered that before, so we can write that down. R equals S. And in the same way we can prove that angle R equals this angle next to it. If these two are equal, the chances are these two are equal. Looks like we can prove that in the same way. So I'll just run through that. That might come in useful. Okay, so let's do something similar to what we did before. So we're going to look at the angle next to R, this angle here. And this angle and angle S are angles in an isosceles triangle. I'm talking about this triangle here. These two sides are the same. So we can state that. I'll call this angle T. So triangle CAB is isosceles. T equals S because they're both opposite equal sides in that triangle. And again, like before, you can see what's happening. Both R and T are equal to the same thing. So that means that R must equal T. Now, I just put a tick on these to indicate that they're equal. I don't put a dot in here because this angle is not the same as this one. But angle R is equal to angle T, so we use a different symbol. Now here is an important fact about parallelograms that I mightn't have mentioned before. If we take the exterior angle of a parallelogram, say we extend this line DC, then we get a pair of corresponding angles. This angle and this angle here are corresponding angles. This angle and this angle here, these are corresponding angles. So in other words, this angle out here is equal to this angle here. So this angle out here is P plus M. Why are they corresponding angles? Well, this line is parallel to this line, and you can call this line here that cuts across those parallel lines a transversal. So as I've explained before, transversal cuts two parallel lines makes two equal angles called corresponding angles. So the angle out here is the same as this angle here, P plus M. And notice that if we add all these angles together, we get a straight angle, 180 degrees. So P plus M plus R plus T equals 180 degrees. Okay, so that's the reason, but what you can do in future, of course, is just remember that, you know, the angles at one end of a parallelogram sum to 180. So these two sum to 180. And similarly up here, these two sum to 180. Now, what I'm trying to do here is prove that this triangle here is a right angled triangle. So I want to prove that this angle up here is 90 degrees. To do that, I want to look at angles M and R. If this angle is 90 degrees, then M plus R should equal 90 degrees, because the three angles add up to 180. So 90 plus M plus R should equal 180. So let's try to prove that M plus R is 90 degrees. Well, we're nearly there now. I want to get rid of P and T. They're not inside this triangle. So we use the fact that M is equal to P. So I can replace this P with M. So you get M plus M here. And R is equal to T, so I will replace T with R. So we showed they were equal earlier, and this must equal 180. So I'm just using this equation. So we get 2M plus 2R equals 180. And if we divide this across by 2, we get M plus R equals 90. And if M plus R equal 90 in this triangle, it means that this angle here, I'll give it a name, I'll call it W. And the reason is angles in a triangle. That's enough. Well, I mean, the three angles sum to 180 degrees. So if two of the angles sum to 90 degrees, then the third angle must be 90 degrees, because 90 plus 90 is 180. So if W is 90 degrees, of course, it means that this diagonal is perpendicular to this diagonal. If this is 90, of course, the one next to it is 90. All four angles formed are 90 degrees. Find the area of a rhombus with diagonals of length 3 and 4 centimeters, and find the length of each side of the rhombus. So the short diagonal here is 3 centimeters and the long one is 4. Well, we now know that a rhombus with the diagonals of a rhombus bisect each other, or well, the diagonals of any parallelogram bisect each other. But for a rhombus, the diagonals are at right angles to each other. So as I just said, the diagonals of any parallelogram bisect each other. So the distance from this point to this point here is half of 4, which is 2. And the distance of this point to this point here is half of 3, which is 1.5. So that enables us to get the length of this side of the rhombus, because we have two sides of a right angle triangle. We can just use Pythagoras. So if I call this x, we know from Pythagoras' theorem that the square of the hypotenuse is the sum of the squares of the other two sides. Now if you work this out, you'll get x equals 2.5. Now all four sides are the same, of course, so all four sides are 2.5 units long, 2.5 centimeters actually. Now how do we get the area of the rhombus? Well, notice that the four triangles are actually congruent. This is 1.5, this distance here is 2, so we have another right angle triangle, sides of 1.5 and 2. Similarly here, of course these are all right angle triangles. The four triangles formed by diagonals of a parallelogram have the same area for any parallelogram, so we could use that fact. In general, the four of them are not congruent though. This one here is always congruent to this triangle in any parallelogram, but this triangle is not in general congruent to the one next to it. Now it is in this situation. For the situation of a rhombus it is. we can see we have 4 congruent right angle triangles. But even if they're not congruent, it's a fact that the areas are the same. That's covered in another video. So if we know the area of one triangle, we just multiply by 4. So we get the area of this triangle here. So we could take 2 as base. Well, if we take 2 as base, then 1.5 is the perpendicular height. So it's half times 2 times 1.5, and we multiply by 4. So we see that 2 times 1.5 is 3. 4 times a half is 2. So we have 2 times 3, which is 6. And that's in centimeters squared.